Instead of load flow with Newton-Raphson method, uh, I prefer to uh, introduce chapter 7 about economic dispatch. The economic dispatch is more easily rather than Newton-Raphson, and I decide to uh, eliminate the Newton-Raphson with the load flow with Newton-Raphson methods for your making easy your study and understanding. But the economic dispatch is very useful, and it is very simple rather than Newton-Raphson. But the load flow in Gauss Seidel is remain, but Newton-Raphson was deleted. In chapter 7, in chapter 7, economic dispatch is related to operation. In load flow, we determine or calculate four parameters regarding to transmission lines or any devices except generators. In load flow, after you run load flow or power flow, you decide that, or you calculate that the bus number I has which voltage and which angle, and after that the pure injection of I and inactive and reactive power injection in bus I we determined. These four parameters is the result of load flow. Another side effect of load flow is finding current. Current flows from bus I to bus J. For example, this is bus I, ZJI connect bus I with bus J, and for finding I or current flows from bus I to bus J with VI minus VJ on ZIJ. All of parameters is vector. And after you find I, you can determine this I or this current is suitable for transmission line or not. The lines has a limitation of a current. We say in power system the thermal limitation of current. Thermal limitation of lines. This means that you cannot follow more than a limit of current in a specific line, and its physical and electrical limitation makes you to limit the current. And so after that you can find that losses, transmission losses, P losses, is a function of current. This is all we catch from load flow or power flow. And so we can determine that all of generators should be supply the loads plus losses. If you can calculate the active power generated by generators is the active power of loads plus the active power that is losses in transmission lines, or reactive power should be generated by generators is reactive power needs for loads plus the reactive power losses in transmission lines. So which subject makes this chapter 7 is important? The subject of chapter 7 is the next step. Okay, we have to produce or supply this amount of active power and this amount of reactive power. And which scenario of generation is based on economic? The total cost of generation is economy or cost effect. So that this chapter that is called economic dispatch. The dispatch is means that you divide power or make a responsibility to a generators to generate a specific power. The economic dispatch means that you have to consider on economy and produce PG with the lower money, with lower cost. Okay, for example, if you have a hydropower power plant, hydro power plant, and thermal power plant like a steam turbine or gas turbine. We know that the hydropower plant is free. The hydropower plant needs no fuel. But the thermal power plant is not free. The economic dispatch makes you to utilize hydropower plant first. And so in power system concept, we divide the hydropower plant and the thermal power plant to base load power plant and non-base load power plant. When you don't have any limitation in water, for example Canada in Canada or in Brazil, we don't any consideration about the water. The hydropower plant should be work, or they would be online, or they should be work in 24 hours. And so the generation of hydropower plant is all the time. If you don't have any limitation or any other issues about the water in dams, this is hydropower plant. The other base load, these are base loads generation, means that these generators or power plant work continuously. Another base load generation is large steam turbine. Because of the mechanical construction of large steam turbine power plants, these kind of power plants need to operate continuously without any interruption. The steam turbines power plant start with many consideration, with many complexity, and you should shut down with overhaul procedure. And so the starting the steam turbine needs more time and is very cost effective. Another base load is nuclear power plant. Because of the basic concept of nuclear power plant, you cannot change the output power of nuclear power plant in wide range, and you should let the nuclear power plant work continuously without any interruption unless the overhaul procedures. As you know, the nuclear power plant is a kind of thermal power plant, but the fuel is different. And so that if your load profile is here, the load profile, for example, is like this, the other amount of power should be filled by by gas turbine gas turbine. The gas turbine started very started and shut down immediately, and its cost is very normal. The gas turbine power plant is cheaper than another turbine, but the ability of gas turbine in incoming and outgoing from the power system makes us to use the gas turbine in the changeable load profile. For example, for this territory, you can to rise or increase the generated power here. You easily you can use gas turbine. This is a fundamental of base load generators and overview of generators. We have to run economic dispatch in this chapter, but in this part we introduced a steam turbine. Steam in Persian we say that bukhar, steam, with fossil fuel like gas, mazout, and the gas turbine and hydro and nuclear power plant. No, then these names is not for your for final exam, but uh, we have to introduce the type of generators or power plant for next calculation beneath. Uh, each generator has a limitation about the active power, the generated active power. The generated active power is limited to max and min. It is not possible to generate zero power, inactive or reactive. The generators cannot generate zero power, and those generators cannot generate more than the maximum limitation of its construction. This limitation is about the active power, and this limitation is about the reactive power. We discussed about power flow. And now we discuss about economic dispatch. If you conflict, if you combine these two subjects, a new subject we have that is called optimal power flow. Optimal power flow, or OPF. The OPF means that you run power flow with the economic concern. Means optimal power flow. The optimal power flow is you think about technical and economical aspect of power systems. So if you want to draw an input and output steam power plant, we can say that the fuel input to combustion part the combustion part make the water to steam, and the steams heat the turbine blades and turns it, and the generator produce the active and reactive power and gives the active and reactive power to the networks. And you should get a connection to internal usage of power plant. In gas power plant, the gas with compressed air, gas with compressed air in combustion part makes the turbine turns, and after that the generator generates the active and reactive power to the network, and you can give a connection or to the internal use of power plant. So the difference between the steam power plant and the gas power plant is only their fuel and in mechanical construction of power plants gives you a thermal rate of fuel. This is thermal rate of fuel. The energy of fuel is called mega BTU. The mega BTU is like joule, calorie, joule. That is energy, BTU. Mega BTU per hour. For example, if you let Siemens to construct a power plant, the Siemens give you this curve, and the Siemens say that if you use that one fuel, you, for example, can get this active power with this mega BTU per hour of that one fuel. For example, if you use a coal, the mega BTU is different to use another fuel. So the vertical axis is mega BTU per hour. That is thermal rate of fuel. And the horizon axis is active power. This curve is determined by a second order equation. The H is alpha 0 p square plus beta 0 p plus gamma 0. And if you get derivative dH on dP, the rate of change of H with active power, we have increment of HR, and you give a derivative from this equation, 2 alpha 0 Pg plus beta 0, and the gamma is ignored. IHR is megabtu per megawatt hour. H, its dimension is megabtu on hour, but the P makes the whole calculation dimension to megabtu per hour, but megawatt. If you multiple the megabtu per hour in vertical axis to a parameter that is called R, the multiplier of R is dollar per megabtu. Each fuel has its cost and its value in dollar. And for megabtu of a specific fuel is the multiplier of R, dollar per megabtu. If you multiple R in the vertical axis, dollar per megabtu, the megabtu is deleted and the dollar per hour is substitute to as a vertical axis here. And you change the graph to the cost of fuel regarding to active power, dollar per hour. That is means that how many dollar, how much money do you spend in hour for producing a specific active power. For a specific active power, how much money, how much dollar you spend in hour. In 1 hour, how much money you spend in producing or supplying this amount of active power. So if you multiple the H with this rate R, we catch cost function. The cost function, and this very famous equation, alpha p squared plus beta p plus gamma. The dimension of cost function is dollar per hour. That is very important that if you produce any active power or Pg is 0, the cost function is not 0. The cost function would be gamma. If you let the Pg 0, this eliminated, that is this term eliminated, and only gamma is remained. So the cost function would not be 0 because the personnel cost is remain, and your investment cost is remain. And if you want to make the rate of generating power, if you want to calculate this rate, you have to find derivative of cost function to active power. The cost function derivative to P is increment of cost function. Increment of cost function or function of cost to alpha P plus beta. The dimension is dollar per megawatt hour. So if you consider the generators out of loads, transmission line, transformers, we collect these three items in a network and separate or get along the generators outside. The cost function of M generators is cost function of generator or power plant number 1, number 2, or number M, alpha 1 Pg1 plug square plus beta 1 Pg1 plus gamma 1 in dollar per hour. The main question is the total cost of utilization of these power plants is sigma CFI, CF of cost function of these M generators with the construction, with the constraint, and the objective function is this cost, that is objective function, but the constraint is considering that the generation of each power plant is limited to its minimum and maximum, and other constraint is the whole generation have to equal to all of demands plus losses. This equation called power balance. Power balance means that the all generation is equal to demands plus losses, and each generator should be limited between its maximum and minimum. Okay, after that we now construct a optimization problem. In power system or engineering, the optimization problem is widely used when you want to find the best way for optimizing a function. You have to write an objective function and minimum minimum that objective function with constraint. That constraint in power system could be minimum maximum of active power or balancing in power or other subjects. So in first step, you suppose that the network losses is not considered or is ignored. The first scenario is ignoring any losses in network. The P losses, suppose that the losses is not exist and the P loss is 0. After that, there are any limitation of active power. The first scenario is the easiest way for only running optimization without any constraint about the limitation of generated power or finding losses. But the balance of power is remained. The balance of power is a basic consideration in this problem. So we want to minimize the cost or minimize the sigma CFI or minimize the sigma alpha p square plus beta p plus gamma for each generator and summing all cost of generators. And only constraint is remain, that is balancing in demand and all of generation. So in finding the optimization and running the optimization, in this book we introduced a traditional method that is called Lagrangian method, or finding the optimal operation or optimal amount of cost function with the traditional mathematical method that is called Lagrangian method. The Lagrangian method says that if you want to optimize the cost, for example the sigma CFI or these equations, you have to write L. The L, the first letter of Lagrangian, is equal to the cost plus lambda times of constraint. The lambda is multiple Lagrangian, or the new parameters, that is produced with Lagrange equations. The Lagrange or L equal to cost plus lambda multiple to constraint. The cost is sigma of cost function of generators plus lambda times of constraint. The constraint is here. PD minus sigma PGI is a constraint. And after that, when you construct or make the Lagrangian, this is Lagrangian equation, the Lagrangian equation. After that, a next step is finding the rate of change of Lagrangian terms to the variable. The variable is Pg1 to Pgm. The round we call round of Lagrange on the round of Pg1 round. This round has a historical background. In mathematics, if you have y is equal to fx as a function of x, when you want to write derivative, you say that df on dx. If you have z, fx and y, the z is depend on x and y, and x and y is independent parameters, and dz on dx is not defined because of the z is depend on both x and y, x and y. So we define in mathematics round z, round x, round z, round y. This is correct. But for this situation in mathematics, because of y is depend only to x, we write that df on dx. So the Lagrange is depend on PGI's PG1 to PGM. So in derivative, we don't say that dl on dPG1. We say that round of L on round PG1. That means that you have to make a derivative from these equations on derivative on Pg1. The Pg1, if you write the derivative from this equation, in this derivative, in this yes, the all of the equation, yes, is important for final exam. You should memorize these equations and its derivative. Yes, yes. Uh, if you want to make a derivative from this term, the lambda and this its minus is comes out, and if you get the derivative from this part, 2 alpha pg to alpha 1 pg1 plus beta 1 is comes out, and this equation is a result of the first derivative of Lagrange on pg1. After that, in pg2 or 2 pgm, we can write these m parameters. So we have m equations, number of equations is m. Another equations is that the derivative of Lagrange on lambda, that makes that this constraint of balancing of power, and this is another equation, and so this is another equation. This is number of equations, and number of unknowns is pg1 to pgm and lambda. This is m plus 1. So in mathematics we have m plus 1 equation and m plus 1 unknowns parameters. In mathematics, this situation makes that we can find a solution. In each equations that is called number 1 to number m, the pg can be calculated like this, and after substitute pgi to this balancing equations, we can get the amount of lambda. So this final solution is very important, and you have to remember that this scenario is P loss is 0 and there are any limitation of generation, and we don't have any maximum and minimum. So in this chapter we have many examples to finding the problems easily. In these examples we have these power systems with three generators, G1, G2 and G3, and its cost function is formulated like this: dollar per hour cost function number 1 for generator 1, cost function number 2 for generator 2, cost function 3 for generator 3. In 8 p.m. in 8 p.m. the total demand is 800 megawatt. 800 megawatt. And this example says that we don't have any P losses and we don't have any maximum and minimum of each generator. And we suppose that each generator can generate ultimately in minimum or in maximum. In this in this in this description, we say that, for example, in this examples, we say that this terms means the losses is ignored. The losses in it is ignored, and the final exam we tell you in the manuscript of uh, um, uh, problems. So losses is 0 and we don't have any limitation of generation. So we have to use these two equations. Lambda is PD, that is 800 megawatt, sigma beta I on 2 alpha I over sigma inverse of 2 alpha I. That is alpha I, that is beta I, that is gamma I. And so PD beta I, that is 2 alpha I, 2 alpha I. So we can get lambda. Lambda says that for supplying 800 megawatts, 800 megawatts, you have to run your power system with $8.5 per megawatt per hour, or operation of your power systems cost $8.5 per megawatt per hour. So for finding which active power in each power plant should be produced, that is PG1, PG2, PG3. The PG is PGI lambda minus beta I over 2 times of alpha I. Lambda minus beta 2 times of alpha is PG1, PG2 and PG3. And if you add PGI plus PG2 plus PG3, you can find that 400 plus 25, 250 megawatt plus 150 megawatt, that is 800 megawatt. That is gives you in manuscript of problems. This is input. This is input of problem. This called alpha, this called beta, this called gamma. Okay, another scenario is about another scenario is about the limitation is considered but the losses is ignored. Losses also is ignored. P loss is 0 but limitation is active. P max and mean. In the previous scenario, this limitation is ignored, but in the second scenario, the limitation is remain. So the cost function is here. The cost function or objective function can be write as objective function OF. OF is remained. The balancing of power is remained without PL loss, and on equality constraint. On equality constraint, it is equality constraint. Equality constraint. On equality constraint is limitation of active power generation between maximum and minimum. Okay. For describe the solution of second scenario, we get you an example. So please consider this power system with 3 generators, G1 to G3. The G1 is based off coal-based generator. The rate R1 is 1.1. This rate is the changing R. We used R to change megabtu per hour to dollar per hour. The megabtu per hour is here. This is a heat rate, and the maximum of active power generator is here and minimum is here. But also P loss is considered 0 as before. The second generator based on Mazout, the heat rate megabtu per hour is here. The third power plant is based off gas, and the heat rate is here, and the maximum minimum is considered like this. And the load is 850 megawatt, P demand or P load. So first of all, we change the equation from megabtu to dollar per hour. If you multiple this rate on the heat rate, or in these equations, you change dollar per megabtu, dollar per megabtu on megabtu per hour, and the megabtu is ignored or deleted, and after multiplying we have dollar per hour. Okay, we find the cost function with R1 1.1 in heat rate, and the cost function is here, cost function of 2 for generator 2, generator 3, power plant 3. And after that we have to find the rate of cost function on active power. Cost function on active power, the derivative of cost function on active power, and we write that here and called it lambda, increment of cost function, number 1, number 2, and number 3. And equal constraint is P demand minus sigma PGI is 0. So we can find that we have 4 unknown parameters and 4 equations. And after that we have to calculate lambda with this equation. Remember that these equations is about when you suppose that the loss is 0, these two equations. By using these equations, the lambda is no $9.148 per megawatt hour, PG1, PG2, and PG3. If you refer to its table, the PG1 is 393 megawatt. 319 megawatt is in range of minimum and maximum. The PG2 is 334 is in range of generator 2, and the PG3 122 is in range of generator 3. So all calculated active power is in range, and the solution is finalized, and we do not any application to make or do anything. This calculation is in range of the minimum and maximum of each generator. But if you, another example, if you changed the rate of R1 to $0.9 per megabtu, and change these items to $0.9 per megabtu, and do the previous procedures, we find that the PG1 is about 100 megawatt, PG2 100, and PG3 32 megawatt. And if you comprise from the limitation we can find that the limitation is not valid for finding PG1. The PG1 and PG3 goes exceed from that table, and so the PG1 is limitation, the maximum is 600, but we get 700, and the PG3 is limited to minimum of 50 megawatt, but we get that 32 megawatt. And how we can do in this situation? It is very easily. If you get, or if you goes beyond your limitation, you set that finding to its limitation. Please pay attention. If you get PG3 about 32 megawatt, the 32 megawatt is lower than minimum. You fix the PG3 in a minimum. The PG3, you determine that PG3 to produce 50 megawatt, and you find that the PG1 is about 700 megawatt beyond of maximum. You set the PG1 on its maximum 600 megawatt. So we can fix PG1, PG3, and PG2 is fine. 850 megawatt minus 600 megawatt minus 50 megawatt. The PG2 is catched 200 megawatt. So that this is the optimal dispatching of active power, and with respecting on minimum and maximum of each generator, and doing the equality constraint for balancing demand and generation. So for second scenario, we do as before, and when you goes beyond your maximum and minimum, you set the value on maximum and minimum. In the next session, we try this third scenario about supposing that P loss is not zero and the maximum and minimum of power plants is not exist. Do you have any questions? Thank you very much. Okay, yes, absolutely. In the next sessions, the next two sessions we have, I try to solve many problems about any subjects we teach you before, and for any problems you have and solving any problems you may be faced in final exams. Don't worry about the solving problems. Okay, okay. In in next in next sessions you can ask your questions, and I am at your service. Okay, okay. Uh, please. Okay, no problem. Please write your problems in WhatsApp, and with uh, um, with any problems you write it in your paper and take a picture, and I uh, gives you a solution in WhatsApp. Okay, okay. In next sessions we discussed over this subject. Okay, we discussed over this subject in next sessions. Yes, in university. Okay. Thank you very much. Thank you very much. Have a nice day. Goodbye.